So welcome to B07 using our packages demonstration video 2 on functions and subroutine. So we looked at a whole variety of functions in R, and we know that they can do different things. So if we want to say we have a string of numbers like the numbers 1 to 10, we can get the mean of that using the function mean, and that is performing particular tasks to calculate the average of those numbers. So that's an example of a function. It's a very and we can write our own functions and we can write more simple versions of functions known as subroutines as well. We can also avail of particular functions that are useful. One of which I think is useful is called p.adjust. So we might have an experiment where we, let's say, take the null hypothesis where we have, if we do a whole bunch of experiments, we expect that the distribution of p-values between 0 and 1 will be random. So if we use the function runIf, that takes in a set of numbers, a start and an end, this will generate 1,000 random numbers in that range. If we look at those numbers, you see that they're different. Every time we run it, they're different numbers. So we can say generate one set of numbers known as x1, and then we can draw a histogram of x1, let's say with a lot of breaks to make it easy to read, maybe a grid. Well, we don't need a grid. Breaks with an S. So that's the number of bins. Okay, that's not very clear. I move my dot over. There, you can see it more easily. So you can see that's effectively random, but not completely random. So each time you run that function, you actually find that it's slightly different. So, and we can create another version of this. So let's do runIf a few times. So just replace runIf, and each time we run this experiment, we'll find that I make the same mistake. Okay, there we go. Repeat that, different shape each time. And we might be interested, for example, in just the ones that are delimited by the p-value going from 0 to 0.05 for complex reasons. And we see the bins there. So let's add more bins so you get more resolution. So you can see it more resolved there. So each time we run this, we actually find that the density of points that fall into this area changes every time. And our problem is that if we run 1,000 experiments and we select those with a p-value less than 0.05, we'll select the ones in this area, even though there aren't actually any effects here. And we can make more complex models where we have direct comparison using a t-test of two different groups to generate this. If we wish, and this is a real problem because let's use the function ORnorm, and we generate values. Let's say 30 values going for the mean of 10, a standard deviation of 5. Look at those sort of values. And if we get ORnorm with more values, ORnorm with 25 values this time, they have a mean of 15, but they have a wide standard deviation of 10. That's two data sets, and we compare them to each other using a t.test, for example. And we can see what we get from that. Each time we run this, we'll get a different outcome. And we can look at the p-dot value we get from that. And you see, if you keep rerunning it over and over again, sometimes you get ones that are low, even though there may be no underlying difference between these groups. So let's say call it 10. And what we can do is put a for loop around this. So we can kind of concatenate our result onto the end of x. But x is not defined. So if we do this, we'll get an error. So x has to be empty first. And then we need to add for I in 1 to 100. Let's say 1 to 1,000. And what we can do then is, just like we had there, is just draw a histogram where here we're looking at x. So these are p-values. And you see there's actually some that are extreme. If you look at it right across the spectrum for x we just made, here, you can see they're random. There's no pattern there. They're just between that distribution. So this is kind of just a quick illustration of our issue of false positives, that all of these are false positives. And if we assume that these are real differences, we'll be mistaken, and that will mislead our research and lead us in wrong directions. So you want to correct for that. So we take that vector x. These are our uncorrected p-values. If we sort and view them, oh dear. Well, we can look at them there. What we want to do is use this convenient function called p.adjust. So p.adjust is a function that takes in the vector of interest, the method, of which, as outlined in the previous class, Benjamin-Hochberg is probably the best because it balances between overly conservative versus correcting using a rank-based method for the expected position of the p-value in the distribution in a null distribution. So it's asking for each p-value when you sort them, is this top ranked one more extreme than you expect on a null distribution? And the same for the second one, and same for the third one, and so on, all the way through the distribution based on its position. So if we put in a length here, we've got 1,000 of them. And what we're going to do is store these in another vector called y1. Let's call it y, actually. And then we're going to do a histogram of y in the same way. And these are the corrected values. We don't need to put in an x-lim. So these are the corrected values. You see that they're markedly different now. So these are the corrected p-values. They're the ones you're going to report to your studies, not the uncorrected values, because that's lying and falsification and really, really stupid. So let's look at the plot of x versus y. So x is our uncorrected and y is our corrected version. You can see that more visually clear now. There, the difference between them. So when you look at that for y in reality, there's very few that actually fit that criteria, but there are some where perhaps there is a true underlying difference, but perhaps there could be false positives, arguably, that this method actually doesn't entirely eliminate. So it's not perfect. Let's look at it. Let's zoom in. Xlim zooms in. So you can see there's not many. Ylm equals 0, 10. Okay, you can see that more clearly now. Yeah. So just 1 and 1 is equal to that value. So if we head and sort y, you can see that's what we're looking at. These two are quite small in comparison to the remaining corrected ones. If you do the same for x, these were their initial ones. So 3 by 10 to the minus 5 was connected to this value, 3 by 10 to the minus 2. So a good rule of thumb for false-positive post-discovery correction methods is that roughly scaled by the number of tests completed. So if you get a p-value of 0.02 and you do 10 tests, it's probably not going to be an extreme p-value at the end. You have to bear in mind that this is important because your p-value incorporates the model that's being tested and the hypothesis, as well as the extremity of the statistic observed. And this can be very misleading when we're conducting research to interpret it as some sort of evidence of what's called significance by some, but not me. So that's p.adjust and a slight rant. There's other handy packages, so you might want more about the stats package, for example. So you can get more information about that particular package and an error for some reason. There's other packages that exist in here, so you might want help about. We just looked at tidyr. You can see the version there. So what's interesting about this, you can see it's updated recently in September 2002. So it's up to date. And you can see that it is compatible with our version 3.1 or more. And you can see the version number that's there as well. So that's useful. You might find that there's packages that are old and you don't want to use them because they may not be compatible with more advanced R versions. You can also get help in these packages as well. So if you do help package like stats, you'll get a very long list of all the different functions that are there. And if you click on one, like ANOVA here, we click on that, we find out details about the method and example. Oh, didn't get examples. So usually there's examples in here, like as.dendrogram. I'm sure if we scroll down, there'll be example code that we can try ourselves. Usually you start with the basic stuff and you can kind of figure it out by using this code, trying to understand it, changing it. All of those things will help you understand it. So what else do we have? We have functions. So a function returns, takes something in and returns something. So it's a type of subroutine. So we can define a function by calling giving it a name. It could be fun1, it doesn't matter. And we're going to call it a function, and that's the special name to use that to refer to this as being a function. We might take in, might have a argument it takes in called num, and that's sent to the function. And then we do something inside here. So we might have num is equal to num multiplied by 2. And then we return our number. So we're just doing something simple here to see how it works. So we're calling our function fun1. So now if we call fun1, we need to give it a number. If we do it without a number, you'll see there we have nothing. It will say there's an error because it's missing an argument. It says specifically argument num is missing with no default. So you give it a number, 33 is sent to that function. So it becomes num. 33 takes in that value. We say 33, that variable is assigned by 33 multiplied by 2, so it becomes 66. And we return 66 back. Oh, so that's what we get back there. So then we could store this in some variable v1, and v1 becomes the output from that function. We could make more advanced functions where we have num1 and num2 and num3, 3 different arguments. We say num1 is equal to num1 by num2 by num3, just for illustration. We return num1, and this function, we're going to call it fun2, is now stored. Again, if we call that like before, with just one number, for example, it will still give an error because num2 is missing. It needs 3 numbers. So if we give it 3 numbers, 1, 3, and 5, it will now work. And gives us returns us 15. And we can store that as a variable if we wish to as well. So this is an example of a function. We're sending information, an argument to the function. The function executes its code and returns information to the line where we are. So you see here in our code, we have this line 241, we have function 1, and we set up the function like this. We're just adding 2 onto x, the input data. That's all. So if we run this code, nothing will happen, but the function 1 will now exist. So when we're down here on line 245 and 246, function 1 is taking in value 1. So function 1, effectively computer goes back from line 246 up to 241, runs these 2 lines of code, and then we jump back down to line 246. So it executes all the lines of code in the curly brackets here and zooms back down here. It's like a kind of teleportation back up to these lines only as defined by our curly brackets, and back to this line. So it goes back to where it started and it defines value 2. So if we run this, we get a value 35, and we can keep calling function 1 as many times as we want. So if we want, we can give it a value 44 and it will return 46, for example. We can give it a really complex thing to do, and it will still return a value. And it can keep doing that. If you have routine tasks, obviously this is quite convenient to do because you can repeat them over and over again, and that will save you time. So that's our example of functions. There's a more advanced term here where we're using strings. So again, if we define some function, what we had before, where we're going to use gsub. So gsub is a way of replacing. So here we're replacing some string. We have some string that we're going to replace with. So let's say we'll use a name, Jane, and we're going to replace that with Jane2. We need an input string, X here, and then we can toggle on ignore case on and off if we wish to. X does not exist here, so that won't be very useful. It's a set of numbers, so that's not going to work. X needs to be defined, so we can just give it a string of names. Let's say James, Jane, Janet, Jenny. So now we run this. It's going to replace Jane with Jane2 in any of the entries in X. So you can see there we have Jane2 and Jane2T for Janet. And in the example here, it's just replacing ATG with M to define these potential start sites in a string of bases, and we can toggle on ignore case if that's relevant for us, because sometimes you'll see DNA in lowercase or uppercase. And this is the same kind of function. We're just returning X. So that's an example of a function. So that kind of concludes this part, and please listen to more on finding useful functions in R in the next video.